architecture search, apart from being something like a tongue twister for my Hebrew accent, is something that for the past 2 or 3 years has been gaining a lot of traction, and for a good reason. Now I'm going to give you a brief overview. It's going to be pretty brief because I want to talk about object detection as well. So a brief overview about NAS. One classic efficient NAS algorithm for classification, and 2 detection papers, and 1 image segmentation paper. Okay, so let's begin. First of all, why search for architectures? As you are well aware, we have gone further than manually designing filters and features for our models. And we are utilizing automatically, we're finding our features automatically, right? So this is the whole regime of machine learning, deep learning. But the focus is now about constructing meta architectures. How do I construct my network? Which layers? How do I connect them? And there is no reason to believe that manual designed architectures are the best ones. So we probably might need to search for the meta architectures as well. Now, in order to do that, I need to define a few things. First of all, I need to define my search space, right? Which architectures can I find in principle? So, for example, if I'm using an architecture that has sequential layers, right? 3x3 convolution layers, for example, average pooling layers with stride 2, fully connected layers. This search space will contain many architectures, one of which is the popular, or used to be popular, VGG16 network that is sequential, has convolution layers, has average pooling, right? And fully connected layers at the end. However, maybe this is not enough. This search space might be too small for me. So I may add multiple branches. I can change the kernel size of my convolutional layers. I add batch normalization, maybe average pools, max pooling as well, dropout, right? So this search space is bigger, a lot bigger, and it can contain one example is the mobile network, right? So multiple branches, I have blocks, I have dropout, everything I need. So after I define a search space, and I'm going to talk about a few examples later, I need to define a strategy. How do I navigate this space? This space might be huge, right? Might be 10 to the order of 20, 30 models. I can't possibly go through all of them, train them from scratch, and evaluate and choose the best one. So I need a strategy. A few popular strategies, or maybe almost all popular strategies, are listed here. The first one is random search. It's pretty self-explanatory. I just sample out of my space and hope for the best. I can use Bayesian optimization, which has been utilized, and it has its advantages. I can use early stopping with random search, which surprisingly is very competitive with the state of the art. I can use reinforcement learning, evolutionary methods, and gradient-based methods. And for the last 3, I'm going to touch upon a little bit later. So I've defined my search space. I've defined a strategy to navigate this space. And now I probably need to define some way to estimate the performance of my model. And this is because, as you are all probably aware, training from scratch and evaluating my model takes a huge amount of time and computation, and I don't want to do that for thousands and tens of thousands of models. So I may use one or more of the following. I can train for fewer epochs. I can use less filters per layer, and then after the search is done, I can increase them. I can use less cells. I'm going to talk about cells later. I can decrease the resolution of my input images, or I can even use different data sets, right? If I'm doing classification, I can use CFAR10 as a proxy data set, and then hope that my model is good enough for ImageNet, if ImageNet is my test task. Another way I can do this is by weight sharing between my models. I'm going to show you one way to do that later. Weight sharing, and then I don't need to train from scratch, and I lower the amount of time it takes to train the model. All right, let's talk a little bit about the strategies. Reinforcement learning is hugely popular in the neural architecture search world. The thing we do here, in reinforcement learning, we have an agent that interacts with the environment. It gets some kind of reward, and then it updates its policy to better interact with the environment later. So we can frame our problem by our agent choosing, its actions is actually to choose one model in our search space. And then the reward is its accuracy, the model's accuracy, or whatever other metric we want, if we want to use inference time as well, etc. For evolution, we have a model. We need to define how to mutate the models, right? We have several evolution methods where we need to either mutate a model or use crossovers, combinations of two parents. So, for example, I can change an operation of one layer from a convolutional with, I don't know, 3x3 a kernel to 5x5, etc. Or I can change the inputs of a layer and thus restructure our model. For gradient-based methods, what we do is we actually form the input of each layer is the weighted sum of all the outputs of previous layers. And this way I have a huge model which contains all possible models, and I place weights on each path, right? And as I train my hypermodel, my architectural weights get stronger or weaker. This is the boldness of the lines you see here. And then in the end, I can choose the argmax of my weights, choose the best path, and I have my model. So reinforcement learning is hugely popular. The problem with this is it's super slow, it's super expensive. The agent usually takes thousands of steps or thousands of models to sample for it to converge. But it is efficient. I mean, it does work at the end, not efficient. Evolution also has its perks. I have an arbitrary way to define how I mutate my models. I can choose how to, which amount of population I use, and all kinds of hyperparameters for evolution. I myself had a lot of fun using evolution methods and a lot of success as well. Problem is, it is still slow. Evolution is randomly walking through my space and hoping for the best in a way, and it's slow. Gradient-based methods are awesome. They're super fast, but they have their problems. For instance, in the original darts paper, I need to contain the entire model, the entire hypermodel in my memory, which forces me to use smaller models. So a few honorable mentions for image classification. We have the NASnet paper, which is the first one to suppress state-of-the-art, manually designed state-of-the-art. However, it was slow, it was super expensive. It took thousands or tens of thousands of GPU hours, which was compared to carbon footprints of 5 people in their entire lifetime, which is crazy. Obviously, by Google, they have lots of resources. They can do whatever they want. We have AmoebaNet, which used evolutionary methods. They also got very good results. About an order of magnitude less computation than NASnet, but still hugely expensive. We have progressive NAS, which used higher and higher fidelities for their proxy, and thus lowered the computation by an order of magnitude. We have efficient NAS, which I'm going to touch about in 2 minutes, which used weight sharing and really reduced the computation cost. And we have differentiable NAS or darts, which is the first one to suggest gradient best. So let's talk about efficient NAS for image classification. They say the original reinforcement learning NAS was very, very slow. And for all the reasons I've mentioned, you have to train each model from scratch. And their solution was to share parameters between the models. How do they do that? Like Dart, they construct a hypermodel that contains all possible models in the search space, and they use a reinforcement learning agent to navigate this, this model. So the reinforcement learning agent's job is to choose a path in this hyper network, and this path uniquely defines a model. Okay? So how does weight training work? Each path that I'm using is sharing the weights or starting from the weights that were learned in previous iterations, if the path goes through some kind of node that was previously learned. So I choose a path, I train this model for one epoch only, then I discard it, I choose another path, I train that model, but I'm using the previous weights if the path intersected. And this way I can train this hypernetwork, and in the end I just choose the best path. Now this search space is that they chose, which was the original NAS space, but in a hypernetwork, was huge. It had 10 to the order of 29 models. So they said, why not use our prior knowledge about how computer vision models usually work, and they employed two kinds of cells. One is a normal cell, which is a smaller network, which has the same output resolution as the input resolution. And the other one is a reduction cell that is another small network that has a stride 2 somewhere, and the resolution goes down by half. And then after they found the two cells, they just injected them into their manually set structure that you can see here, and they had their model. The strategy they used is a reinforcement learning agent. And the proxy, like I've mentioned, is weight sharing, so they do not need to train every model from scratch. I hope you can see some numbers. So the results are pretty impressive, if you can see. If not, you have to trust me. So they show, first of all, that using the smaller cell space, which is already only 10 to the order of 15 size, navigating this smaller space is better, even though it's smaller, and possibly the best quote-unquote model is outside of the space. It's easier to navigate. So they got a better result with the cell structure. You can see that they have almost the same results as the original NASnet, but they have, I think, 3 or even 4 times, 4 orders of magnitude less computation time, right? So instead of thousands of hours, they used only 1 GPU for 16 hours. OK, let's talk about object detection, because image classification is really cool. It's nice. We like it. But we have other things on mind, right? So let's talk about NAS FPN. A brief overview of how feature pyramid networks work, for those of you who are tired or unfamiliar. For detection, object detection, we need a backbone model that is usually pre-trained on ImageNet for classification tasks. And we need it to extract features from it and put it in our detection heads, our classifiers, regressors, etc. And we need it multi-scale, right? So we have our backbone model. We pass our image in it. It gets, our layers gets deeper and deeper. The resolution gets smaller and smaller, and they are semantically stronger as they go, as we go further deep, right? What the feature pyramid network guys say is, OK, we need to enjoy the best of both worlds. We want both spatially good resolution for our features and semantically strong features. So what they devised is a way to merge all the layers. Okay, so what they did is they took the deepest layer, they upscaled it by 2, and they merged it together with the previous layer. And then they repeated this process until they had their merged features. And then we use these features as input to our detection heads, which works well. And we like it. And everybody uses it. But who says that merging the deepest layer with the one previous and then repeating this process is the best way? This is some human bias we introduced into the system. And you probably noticed that this is the motif here. This probably is not the best way to merge the features. So first of all, how do we define the feature pyramid network outside of the original FPN paper? We say we have a backbone model. We want to put it in some black box, which we call the feature pyramid network. And we want the features to be merged in some way for our detection heads. So what they did is they defined a merging cell, which its input is 2 layers from the backbone model. They choose one of many operations to perform on these layers, and then they combine them using either sum or pooling or whatever you guys want. After we define this merging cell, we can put the output of the cell into our pool of available layers, and then the next merging cell can choose the output of this cell as its input, or it cannot, but this is the search space, right? So the space contains all feature pyramid networks that have some backbone model which we don't touch, and can be constructed by n merging cells. The n is set in advance. The proxy they use is to train for only 10 epochs on Coco dataset. They use a super small backbone model, ResNet-10, and they reduce the size of the input image. So everything will be a lot quicker. Obviously, whenever we use a proxy like this, we really cross our fingers and hope, quote unquote, sorry, that there is a strong enough correlation between the proxy output and the output of the model if we had trained it on our task. The strategy they use is, again, a reinforcement learning agent. This is some details. After every merging layer, we put in some ReLU conv bench normalization just to make things interesting, to make it a little bit more agile. We adjust each layer. The layers probably have different spatial resolutions, so we adjust that by upscaling or downscaling if needed. And they suggested to use one of 2 binary operations, sum or global pooling. And this is the model that they got in the end, which is very, very colorful, but it's not, wait for you to take a picture. OK. It's very, very colorful, but it's easier for me to explain it using a diagram. So what's going on here? It's a pretty neat way to explain what the FPN looks like. So if you look at the top left diagram, what we can see here is on the left we have the dots that are circled with a green circle, and on the right we have red circles. So the green circles represent our input layers into the feature pyramid network. They're actually the exit layers of our backbone model, going spatially, going deeper and deeper from the bottom up, right? So the bottom left node is the most shallow layer of our backbone exit layers. Then we go deeper and deeper and deeper. We go up in the diagram. And you can see that the deepest layer is upscaled and connected to the previous layer. And then this output is upscaled and connected to the previous layer, et cetera, et cetera. And this is how the original classic FPN looks like. Now, their reinforcement learning agent tried to come up with better and better ways. And you can see as you go to the right and then on the bottom row that it devised different ways to merge the layers. And the bottom right diagram represent this model, right? So this and the bottom right are equivalent. And you can see that it learned to utilize the outputs of its previous merging cells, which at the beginning it didn't do, and that's probably a good thing, but it's all automatic. We have search hyperparameters. I can choose how many emerging cells I want. I can choose maybe a different number of output features for my FPN. I can choose different backbone models, right? Because my FPN is agnostic to my backbone model. And the results are pretty promising. They show that they both achieve state-of-the-art accuracy, and they can even compete on low latency models in the mobile context. Also, what you can see here is that they show it's better for us to utilize the NAS FPN network to increase accuracy instead of increasing the backbone model. So you can look at the ResNet 50 FPN that's smack in the middle there, And if I increase it to ResNet 101 as the backbone, I gain 1 point, like 1% in my average precision. But if I utilize the NAS FPN instead, I can get 3 average precision points, which is awesome. However, let's talk a little bit about the cost. So Google being Google, they don't mind, they don't care. Training each model on the proxy data set takes 1 hour on a TPU, and their agent took around 8,000 samples, 8,000 models to converge. So 8,000 TPU hours, which is, Google. Okay, so that was one way. It works, it's great, it's costly. I can think of 7 different ways to make it better, and people are probably working on it right now. Let's look at another way. So let's look at NAS, which is not Google. So the motivation is, again, that object detection usually requires either pre-training on ImageNet or using a much longer training time to train on my detection task. Also, this breaks down on smaller detection data sets. So NAS FPN, they bypass this problem by just not touching the backbone model. They said, OK, you pre-train your model, you give it to us, we'll do the rest. The guys at NAS, they say, I don't want to do that. I want to change my backbone model. So what they do is they build a super network like NAS that contains all possible models, right? And then they pre-train this super network on ImageNet. Then they use the entire super network and they fine-tune it on the detection task. Okay, so doing this entails choosing a path in the model, adding my feature pyramid network, adding my detection heads, and going for an epoch or 2 or whatever you decide for your proxy, and then choosing a different path, et cetera, et cetera. And at the end, you get a super network that is well-trained. And in the end, after I have my super network pre-trained on ImageNet, I search for the best model or the best path in my supernet, and I don't need to train it any longer because arguably my models are already trained. Right? There are a few caveats like batch normalization, but we'll leave that for now. So what are the dimensions? The search space is all the backbone models consisting of shufflenet blocks or exception blocks, which was their choice. Why 40? Because that's what they used. It's obviously not optimal, but you can't do everything at once. The proxy is sharing weights like NAS, like efficient NAS that we've talked about. And the strategy is using an evolutionary algorithms. So they mutate and they cross over their path in order to find the best one. They don't really delve too deep into it. So we don't really know exactly what they did. And just as a side note, all in all, this paper is not ripe yet, in my opinion. They have a lot of details missing, like ablation studies, etc. And also, the results are not so impressive. They show that they have 0.8 points better than using the original ShuffleNet v2. In my experience, that's pretty much the standard deviation. I don't know. But it's super interesting. They're the first ones that I saw that tackled the backbone model search in object detection. So that's something to keep an eye on. And also, in terms of cost, it's way lower than the NAS FPN, even though it's still a lot higher than image classification. OK, so these were 2 examples about object detection, 2 different ways to tackle this, search space. Now let's talk a bit about one really interesting example of doing NAS for semantic image segmentation. So the motivation is everybody is working on classification. Classification is nice. We want to do something else. They noticed that usually we follow a 2-level hierarchy, right, where the outer network level is set in advance. Like I talked about before, I set the number of cells I want to use. And then we only search for the cell structure. However, they say this is obviously not optimal, not even for classification. But for dense image prediction, we know that the model is very sensitive to the spatial resolution. So what they suggest to do is to use a two-level hierarchical search space and search for both the optimal cell structure and the optimal network structure simultaneously. And they do that by utilizing or extending the DARTS method. Right? The DARTS, which I talked about earlier, is the gradient-based method where you place weights on the inputs, and every node's input is the weighted sum of all the previous node's outputs. And I use these architecture weights in my loss, and they get stronger and weaker as I train. So they note that the spatial resolution of the next layer in most image segmentation networks is either the same or it's twice as big or twice as small. So what they do is they design this trace-like diagram where each layer is connected to the next layer, which is either twice as big, twice as small, or the same spatial resolution, right? And each blue dot here is actually a cell, a small network that I'm trying to find the best structure for. Now, the cell structure is shared amongst all nodes. So I have only one group of parameters for my cell, and I have the network parameters per node. Here are a couple of examples, or 3 examples for known networks, known image segmentation networks, and how they would look on this trellis graph. Right? So DeepLab v3 only downsamples. You have the conv where you have downsampling, then upsampling, and the stacked hourglass where you downsample all the way, upsample, and then do it again. So their goal is both to find the best path in this structure and also the weights for the cells. And I've managed not to put any Greek letters on my slides up till now, but here they are. So this is just writing down what I've talked about. The cell's input is a weighted sum of all the outputs of the previous cells. And we have 3 beta parameters that control the weights of the cells, which are twice as big, twice as small, or the same spatial resolution from the previous layer. Now, to optimize this, I alternate between updating my network weights and updating my architecture weights. After training is done, for my cell structure, I keep the strongest architecture, which is exactly like DARTS. For my network, I can use my the classic Viterbi algorithm. Where's Gil? Yeah. I'm sorry, we worked on this like 7 years ago in our undergrad about Viterbi. So we use the classic Viterbi algorithm to find the best path. Why is this? Because each node has 3 beta parameters, which are both positive and sum to 1. I can regard them as probabilities of transition, which is exactly what the Viterbi algorithm was designed to do. And this is the results. This is the structure they found. Note how it downsamples, then upsamples. And it would be really hard to just think about that manually. And the cell structure that they found to be best. And the results are interesting. On the one hand, they show their results are much, much better than other state-of-the-art networks that were not pre-trained on ImageNet, right? However, they are not state-of-the-art versus networks that have been pre-trained on ImageNet. Right? So they show a lot of promise, but it's not groundbreaking as of yet. They show it on a few different data sets. You can see that these results repeat themselves. They do beat some of the popular models, but not all of them. So what they basically did is they extended DARTS, or the gradient-based method, to image segmentation. They do not require ImageNet pre-training. It's pretty fast. It takes only 3 GPU days to reach their conclusion. And it could be extended in many ways for other tasks, like object detection. So what I want you to take away from this is, first of all, maybe you didn't know, but most computer vision NAS work is geared towards image classification. However, we can see some work being done towards object detection, semantic segmentation, and other CV tasks. And each computer vision task has its own complexities, and it needs its own ways to tackle this. What people usually do is they take the classic from 2 years ago image classification methods of tackling the neural architecture search, and they extend it to object detection and the other tasks. That's it. So the question was, how do we not overfit with our search? Obviously, if I'm training 8,000, 10,000 models, I'm going to overfit something. And the answer is that you use one data set to train each model, and you use a different data set to train your reinforcement learning agent or your evolutionary methods. Okay? So you do not overfit on the same training data set. This is the way we tackle it. All right? Thank you very much.